All right, let's go over some more examples of using this fundamental theorem of calculus part 2. For the first example, I just want to reiterate the basic idea. If you take a function and you were going to define an accumulation function, say the integral from -3 up to x of t squared plus 5 dt, whatever. When you take the derivative of this accumulation function, what we're going to get is that integrand right back again, but with x plugged in place of t. This would be x squared plus 5. And that's it, right? The derivative of this accumulation function is equal to the original integrand. Okay, but it gets a little bit more complicated. For the second one, let's define our capital F as the integral from x up to 5 of sine of t dt. I'm just picking up some random integrand function here. I picked sine this time. All right, well, this is the negative integral from 5 up to x sine of t dt, right? So in order for us to use the fundamental theorem of calculus, the x does have to be on the top. Okay, in order for us to use the formula, the x has got to be on the top. It's got to be constant on the bottom and x on the top. So then we can do what we can apply the idea of derivative here. This is not equal, but if we do the capital F derivative, then what we get is this integrand with x plugged in, but this time it's going to have a negative on it because we had to adjust the order to get the x on top and throw a negative on there. So that's a little bit of a variation. Let's look at another variation. Let's say you are working with an integral from 0 up to x squared, and then the function inside here is, let's say it's like t minus e to the t or something, dt. Okay, this one is a little bit tricky because what we have here is sort of like the accumulation function is composed with this x squared. So instead of just x, it's x squared, right? You could think of this as like 0 up to u, t minus e to the t dt. And the derivative of this with respect to u is going to be u minus e to the u, which would be just the integrand function with the u plugged in. But we want the derivative with respect to x. Okay, so taking f with f prime here with respect to x, we can do the derivative with respect to u and get, here I'm going to use u equals x squared. So we're going to have x squared minus e to the power x squared. But then the chain rule would say, the chain rule for derivatives, right, would say, okay, that's the derivative of the outer function. Now let's multiply by the derivative of the inner function, which would be the derivative of the x squared, which is 2x. And there we go. There is the derivative of this function. So we defined this. It's a composition of an accumulation function with another function, x squared. So we differentiate it the same way we differentiate any other composition, which is apply the fundamental theorem of calculus like it's a differentiation rule to tell us the derivative of the outer function with the inner function still plugged in there, and then multiply by the derivative of the inner function. So that's what the times 2x is. Okay, so yeah, so this really highlights how the fundamental theorem part 2 can really be basically used as a differentiation rule and combined with other differentiation rules if you want to. Okay, I'm going to go over one more example. For this example, I'm going to get myself some more space here. What is this problem? This is example 4. Yeah. So for this one, let's do capital F of x is the integral from x up to 2x. And we're going to do t to the 5th dt. Okay, so in order for our fundamental theorem of calculus to work, the lower limit of integration has to be a constant, and the upper limit of integration is the variable, right? And then we can say the derivative of that is f of x. This is different. Here, we have both the lower and the upper limit of integration are functions of x. Okay, that's going to be a bit of a problem because this will not apply right away. But what we can do is we can split this up into two integrals. We can go from x up to 0, t to the 5th dt, and then add the integral from 0 up to 2x, t to the 5th dt. top limit of integration matches bottom limit of integration, so they can be added together and combined, right? This is one of the properties of integration we learned. Adding two integrals with matching limits of integration can be combined into one integral. So this looks pretty good. All we got to do is take the first one here and swap the order. So we've got to flip that around and make it negative. Negative 0 up to x t to the 5 dt. And then plus the integral from 0 up to 2x t to the 5 dt. Okay, now we're ready to take a derivative. So capital F prime, we're going to get the negative derivative of the first integral, 0 to x t to the 5 dt, plus the derivative of the second integral, 0 to 2x t to the 5 dt. This first one is pretty easy because I can just apply the fundamental theorem part 2 as a differentiation rule. I can apply it directly and take the x and stick it in there and get x to the 5th. And that's it. The only other thing is I have this negative, right? I have this negative here. Okay, so that first term is pretty straightforward. The second term, just like the previous example where we had the x squared in there, this is a composition of functions. So we have the function 2x plugged inside here. So what we have to do is apply the fundamental theorem as the derivative of the outer function and put 2x inside of this integrand, 2x to the power 5, right? So that's what we get first. And then multiply by the derivative of the power of the function 2x, which would be just 2. So overall, this is our derivative that we get. Negative x to the 5th plus 2x to the power 5 times 2. And this can be simplified if you want to. I guess 2 to the power 5 is 32, so times 2 is 64, minus 1. This should be 63x to the 5th. And that's it. That's the derivative. So I hope this this kind of shows you how you can use the second part of the fundamental theorem of calculus, like a differentiation rule, to help you take derivatives of functions defined in terms of definite integrals, like these type of accumulation functions, or some variations on accumulation functions, like this one. Okay, so yeah, I think that'll about do it for this video.